we introduce paper in motion, a method for seamless point-level 3D scene interpolation. In this work, we introduce a novel problem setting called point-level 3D scene interpolation. Given RGB images of a scene from multiple views at two different states, the goal is to synthesize a smooth interpolation between both the scene geometry and the appearance. This problem is very challenging for a few reasons. First, there is no ground truth supervision for the intermediate states. This is different from the typical dynamic scene reconstruction setting, where the scene is observed at all times. Second, in contrast to interpolating rigid parts of articulated objects, point-level interpolation allows points within the same part to move freely, and so each part can deform non-rigidly. Last but not least, the scene changes between the start state and the end state can be drastic. To address these challenges, we leverage a recent point-based neural renderer called Proximity Attention Point Rendering, or PAPR. At a high level, PAPR learns a point-based representation of the scene, where the geometry is represented by point positions, and the appearance is represented by a feature vector associated with each point. To render a view, PAPR shoots rays through each target pixel, and renders them using an attention-based differentiable renderer. This design is crucial as it enables several key advantages over the commonly used splat-based methods, such as Gaussian splatting. To render a point cloud, splat-based methods associate each point with proxy geometry such as a Gaussian, and project the proxies onto the image plane. However, if a distant pixel has high loss, no splat will have significant contribution to the pixel. As a result, no splat can be moved to cover the pixel. In contrast, attention-based methods like PAPR normalize the total point contribution to 1. This ensures that there are always some points with significant contribution, and this allows PAPR to learn large scene changes. Another advantage of PAPR is the ability to handle non-rigid transformations. Since Gaussians cannot be bent, Gaussian splatting may introduce gaps under non-rigid transformations. In comparison, PAPR interpolates nearby points to render, and so it automatically adapts to these transformations. To adapt PAPR for scene interpolation, we propose to first train a PAPR model on the start state and use it as a scene template. Then, we fine-tune this scene template using images from the end state. In particular, we first fix all the scene template parameters except for the point positions. The intermediate checkpoints of point position during the optimization process then serve as the interpolation of the scene geometry. Once the geometry has converged to the end state, we further fine-tune the point feature vectors and the attention model weights to capture the appearance difference between the start state and the end state. To render an intermediate state, we use a convex combination of the model weights between the model at the start state and the model after fine-tuning. The weights we use to combine depends on how close the state is to the start and end states. For the geometry interpolation, however, if we naively fine-tune a PAPR model, it will fail to preserve the geometric structure of the scene. To address this issue, we propose two regularization techniques. The first one is a loss that encourages local rigidity. Specifically, for each point, we first find its k-nearest neighbors in the start state model and calculate the L2 distance to each of its neighbors. Then, at any subsequent time step, we add a rigid loss that tries to preserve the distance from each point to the same neighbors at the start state. Since the first loss does not consider the direction of motion, we further add a regularization step to encourage local uniform movement. Specifically, for each point at each time step, we record its displacement from its initial position in the start state. We then adjust this displacement to be the average displacement vector of its k-nearest neighbors in the start state. As shown here, these two regularization techniques can preserve the object's geometric structure effectively. Let's see more results. We compare our method to the latest dynamic scene reconstruction method, dynamic Gaussian, on this novel task. Here, we can see that the baseline fails to bridge large scene changes at the butterfly wings, whereas our method produces a smooth flapping motion. Here we show a case with non-rigid stretching motion of the dolphin's tail. We can see that our method generates smooth rendering during the interpolation. As shown on the bottom left, our method is even able to capture the gradual change in the shadows cast on the board, showcasing its ability to produce realistic appearance interpolation. For more results and code, please visit our project page. Thank you.